we talk about loads, and synonym for loads is forces, right? We have two different types. We have concentrated loads, and we haven't talked about this terminology. We've talked a little bit about it, but not too much. The other type of loads are distributed loads. Do you remember what the synonym was? You used it in physics for concentrated loads. What are concentrated loads? What are concentrated loads? Have you heard that term before? A point load. Have you not heard concentrated load? But you've heard a point load. Is that what was used before? Okay, so concentrated loads, and sometimes I just abbreviated it like this. Do you remember in chemistry? What does this represent? The concentration of something? Yeah. So my abbreviation for concentrated is that. But this is a point load. And what's a point load?
All the forces act on one point.
Right, force, and not all the forces. We're just going to say a concentrated load. Let's make this not plural. Okay, I just made it all singular. Hang on. So force acts on one point. Is it echoing here? Santiago, just wait a minute. So what do you think a distributed load is? It's not acting on one point, right? What is it? It's spread out, right? So you walk in the snow, which I'm hearing there's not really that much snow up in the mountains. You walk in the snow and you have a certain weight, let's say 150 pounds, right? And you step and you might sink, right? But if you put snowshoes on, you don't sink. Well, what did you change? You didn't change your weight. You changed the surface area that that load is distributed over, right? So we could distribute a load over, we could distribute it over an area. Distribute it over an area. So let's draw that. So we take a load, and this is my area, and I have it's distributed. And what is that called? Those of you in materials, when you take the force and you divide it by the area, what is it called? Those of you in materials? Stress. And what was stress abbreviated? Do you remember? Little sigma. But I also heard, what's another word for force divided by area? I heard somebody say it. Starts with P?
Pressure.
Pressure. So what's important for us to know is when do you use the word stress and when do you use the word pressure? Do you know? I don't know if you talked about it in materials or not. What?
Solids and fluids.
Right. So you use the word stress when we're talking about solids. Could you guys see over there? Well, you can just get up, TJ, if you can't see.
Okay.
But pressure is used for fluids, which means, what's a fluid? Liquid or?
Gas.
Liquid or a gas. Let's say air. So you talk about air pressure in a bicycle tire. You don't say air stress in a bicycle tire, right? You say water pressure going through a pipe, right? But the word stress is used like right now, am I putting pressure or stress on the ground? Stress. Why? It's a solid. Okay, so you use the word stress. So in lay terms, walking around, we say pressure sometimes when we really should be saying stress, but now you know the correct words. So use the right words. Okay? So this is when it's spread over an area. But there are times, and in statics, what we see more often is spread over a length. So for instance, you have a beam. And you have a beam, and the beam has a certain length. And we're applying a force over a length. And it's what's this little W? Is that omega?
Yeah.
Yeah? Okay. So omega represents the load that's distributed over the length. Now, if you talk about a beam as being a beam three-dimensional? Yeah, everything we design is three dimensions. I mean, is anything two dimensions? I guess a piece of paper is, we could say is two dimensions because it's so thin. But a beam is 3D. But we could simplify things. We could say, okay, yeah, it has a depth, but we're only going to look at its length. So we're going to look at the force divided by its length. So we're going to see this in statics about halfway soon. Well, maybe halfway through the course. We're in week 3, is that right?
Yeah.
Okay, so concentrated loads, distributed loads. And we could also add that this is an example of a uniformly distributed load. Right? The load is supposed to be, I mean, it's not perfectly horizontal, but it's supposed to be. That's a uniformly distributed load. Makes sense, right? It's a distributed load that's spread uniformly. Here's a beam and the load is some weird thing. So is this uniformly distributed? No, it's non-uniformly distributed. Okay? So what we're looking at right now is we're looking at terminology. Okay. What was one type of point load we've seen so far? We've talked about it all the time. All forces converge on a certain current. Concurrent. Concurrent forces. And concurrent forces are forces that are all acting on a single point. And are they concentrated points? Concentrated loads? Yes. Are they point loads? Yes. They're not distributed. Okay, Santiago, I'm hoping that I answered your question.
Yeah,
But maybe
that was my question. What was the difference between concurrent forces and concentrated
Okay.
forces?
So concurrent is an example, should we write that? It's an example of a concentrated load. But we're going to see some now that are not, they're concentrated, but they're not concurrent. And that we know, if we only have concurrent forces, what's the only type of motion that could be applied? Translational. It's only when we have forces that are not concurrent that causes things to rotate, right? Okay. So let's take a look at some examples of different types of forces so we get some more terminology down. Yeah.
Is it still called stress when it's force over length?
No, it's not. It's not. It actually does not. I am not familiar with the term for that. I've always referred to it as force over length as an engineer, as an engineering student, and as an working engineer. It's represented by this thing, but they don't call it omega, they don't call it W, they don't call it. So it doesn't have a name. So when it's over area, that's when you call it stress or pressure, but when it's over length, I've just heard it referred to as force over length. Okay, so we're looking at one of the sheets then that you have. Everybody should have 3 sheets now. So Sam, where's Sam? Just walked in. There are 3 sheets that went around. Maybe go down. Taven, are you the one? Maybe is your area where the extra sheets are? Oh, okay, down here. Okay, so let's take a look at. We're going to go around the room. Radian, let's start with you. So for this first picture right here with the car, they're already telling us, right? This is not a distributed load, right? They took the loading of this car and they divided it into what? Radian, if they took the load of the car and they divided it into two different forces, okay? Notice there's an F1 and F2. When you have a variable given as F1 and F2, you know that they're not necessarily equal, right? If they called it F1 and F1, then you would know that they're equal. You know that already. How many wheels are on a car? 4. So we really could have put 4 forces there, right? But we're looking at it as only a 2-dimensional object, which is the same as this guy right here, where I'm dividing the force over the length on the beam, even though I know a beam is 3-dimensional. Many times in statics, many, almost all the times, as an engineer, you're always simplifying problems. And by dividing the load into two, I'm simplifying the problem, because the forces it's experiencing on this side that we see is the same as the forces on the other side, as long as there's not, you know, an animal or a collision or something on one side, right? So these are called concentrated loads. What else could we call them? Point loads. Okay, let's look at the next one now. All these forces, F1, F2, F3, what are they? Are they concentrated? Yeah, these are concentrated loads. Are they point loads? Right, they're concentrated loads, they're point loads, and what else are they? Concurrent, we already know that. They're all acting at the same point. Okay, we're introducing another one now. Collinear. What do you think collinear is? Forces act along the same line. Along the same line. Are these forces concentrated forces? Are they concentrated? Remember, the option is they're either concentrated or they're distributed.
Yes.
They're concentrated. Distributed means they have to be spread out. They're not spread out, right? It's still one. It's concentrated because it's one, it's whatever all the forces, it's acting right along this line. It's one force. It's not distributed over a length or an area. So it's a concentrated load. What was that?
Didn't that create rotational motion? Those forces?
Well, we're not, only concurrent is the one that doesn't,
Oh,
right?
okay.
A concentrated load is just a point load. So is this also a point load?
Yes.
Yeah. Is it a distributed load? No. Have we seen distributed loads anywhere here yet on the left side? No distributed loads. They're all concentrated. It's either concentrated or distributed. So they're concentrated, they're point loads. Can I say it's acting here? Can I say they're both? Let's call it F1 and F2. Are they both acting here? Yeah, because it's along that line. Right? They're collinear. They are acting along the same line. Can I say they're acting here? Yeah. It's still the same magnitude and it's the same direction. It's still the same vector. Okay, let's take a look at this one. So, are these concentrated loads or are they distributed? Take a look at what it says. F1, F2, F3, F4. Are they concentrated on a point? Yes. This is concentrated right here. This is concentrated right here. This is concentrated right here. And this is concentrated right here. They're all concentrated forces. Are they point loads? Yeah. Now, coplanar. This is the one that's a little bit more confusing. It's forces acting in the same plane. And I got this confused many years ago. Think about what's the difference between when I say forces acting in the same plane or forces acting on the same plane. Talk to the person next to you. What's the difference between when they're acting in the same plane or on the same plane? You think in and on, those two words have probably never been that interesting to you, right? In, on, who cares? One different letter, big deal, but it's a big deal here. Forces acting in the same plane versus forces acting on the same plane. So talk to your neighbor and figure out what the difference is.
Yeah, that's what I think. I think on is like, say I'm just like, this is plane. On is going to be like, they're all on that plane. But I think in is saying that, like, say this is the plane, all the forces point towards their points are in this plane, but they could be going different directions. One could be going like that, one like that, like that, like that. But I think on, they're like literally all just like pressing down, like playing. They're all kind of in the same place. I think it's more like a directional because you know some are going down and some are sideways, but they're in the same plane. They're in this plane. They're not on that same plane because the one like this is in the plane, but it's hitting a plane that you can say slicing through. I think that's what it is. But